Good morning, Bruno. You've developed the Imagine project. Can you tell me a bit of background and overview of the project, please?
Yeah, sure, I can. The Imagine project is something completely new, I would call it. It is a try to get nuclear solved as a demand problem. So we have a demand that is we need energy, we need net zero energy in huge amounts. So it is the aim to design the optimal nuclear system to deliver cheap, affordable, and reliable energy for the world.
Thank you. I understand that the project is based around the molten salt reactor technology. How does this technology compare to other types of nuclear electricity generation?
Yeah, it's a different technology. In every reactor we operate in the world in the moment, we have solid fuel in the form of ceramic pellets, and this is a kind of limiting since the pellets have to be produced. When you want to close the fuel cycle, you have to reprocess these pellets. So the idea was, can we not do it easier? Can we not have our fuel in a liquid form where we can put things in and put things out during the operation? We can more or less bring the whole fuel cycle into the reactor instead of putting stuff into the reactor, waiting for years to cool down, then reprocess, then invest much money to create again ceramic fuel and bring it to the reactor. So I would call it an integrative system where everything is within this one system from the beginning of life of your fuel till the end of life of the fuel, and the outcome will only be fashion products. It's a bit like if you would say you make a wood fire and at the end there's only ash coming.
I see. All right, thank you. Can we recycle the output material from the molten salt reactor?
No, we can maybe, but it is not like in a normal nuclear reactor. In a normal nuclear reactor, you would say you recycle the outcome material. The outcome material is the spent fuel assembly, and you recycle it by making uranium-238 and plutonium accessible again. But since these things are not coming out, this classical recycling you can't see in this form. What is there is another opportunity. The cleanup system will work completely different. So we will get radioactive fission products out, but sorted in elements. And we have, for example, opportunities to reuse them. But reusing means in this moment we find a good use for the materials and not recycling it back into the reactor, since it would be like in a coal fire or wood fire. You throw the ash back into the fire, nothing will happen anymore since the energy is taken out. So it is not this classical recycling as we see it, but reuse of materials. I think we will reach a new level and new great opportunities.
I see. Very good. As the molten salt reactor will be fueled from nuclear waste from current nuclear power stations, how will this process reduce the level of radioactivity of the waste?
It will more reduce the volume than the radioactivity. The radioactivity itself is a kind of physical constant. So this level will not change. Per energy you produce fission products, and the amount of fission products is clear through the energy bound in the binding energy. But what you see different is that you don't declare huge amounts of potential fuel as waste. So the uranium-238, which makes 95% of your spent fuel in a light water reactor, is not declared as waste. So the amounts which will come out are much smaller, the volume, but per energy, it's the same amount of fission product which is produced, which is just, I think that is physics we can't change.
I see. I've read that there's currently enough nuclear waste material in the UK to fuel the molten salt reactors set for 7,500 years. How does this compare to other energy sources?
Oh, that's a good question. How does it compare to other energy sources? So let's think about this a bit more. That is interesting. So when we burn completely 100 kilograms of uranium, so that's not very much. Think about uranium is a heavy metal, so it's about the volume of about 10 liters. We can produce 1 terawatt hour. That's a rather abstract number, but to give you a feeling, 1 terawatt hour delivers for the UK about 30 hours of electricity for the whole UK. So that's a tremendous amount of energy out of these 100 kilograms. If we would like to produce this energy in a light water reactor, then you would need about 2.5 tons, so a factor of 25 more of nuclear material. But I think what is much more impressive is you would have to burn 350,000 tons of coal. That is the dimension of energy you have in these 100 kilograms. So the outreach of uranium would be limited if we use it in a light water reactor. But when we can use it in a molten salt reactor, then and can operate as we promise and imagine, then we have a tremendous energy reservoir. And it is only material which is already in the UK, which is stored and declared as waste. It doesn't mean we dig for new uranium. If we would start to dig for new uranium, as we do it every day, then these amounts will get even larger.
I see, yeah, so it sounds much better. Just one last question. How will this new technology affect energy costs for the public?
Another really good question. I think there are many molten salt reactor developers who bang out numbers. I don't want to bang out numbers. I think there are too many unsolved or undeclared things which we have to keep in mind when we want to do it. I would like more to look into the cost for the society. That is, I think, more of interest. The cost of the society is defined by things like pollution, by things like cost of waste storage. Let's start with the pollution. When we don't dig for new uranium, since we use resources which are there, we will reduce the pollution due to uranium mining to zero. That is a cost for the society we should not forget about. When we are able to produce a waste matrix where we at least have only a factor of 20 less volume in the waste, then the waste storage will get easier. When we handle the waste different and we can reuse material, it will get even easier. So at this end, we save money for the society. And then when we think how much reprocessing costs, when we don't need to build a reprocessing facility for closed fuel cycle, it's again, that's normally societal investment. Sellafield was built by the government. And the cost is in the area of 200 billion pounds to rebuild Thorpe. That was what my colleagues at NNL told me as a rough number. So these are sums of money we save when we make it possible, and what at the end will be the energy cost of the facility per terawatt hour or per megawatt hour. That will very much depend on the design of the facility.
Nice.
Thanks, Trevor, for the questions.
Well, thank you very much. Very interesting. Thank you.